When you hear the word satellite, you might think of a remote object traveling thousands of miles away in space, impossibly far from any living thing. But here on Earth, a big part of our economy depends on them.
People have no idea how much of their daily life is touched by satellites.
That's Rachel Jewett. She's the managing editor of Via Satellite, a trade publication for the commercial satellite industry.
Cruise ships use satellites. John Deere uses satellites. The government uses them. All of the apps that you use that have GPS, like Uber or DoorDash, anything like that, that's using the GPS satellites. The weather forecast, part of that is coming from satellite data. Your broadcast TV, if you're on a cable network.
Getting these satellites up and working is a big job. It involves a complex manufacturing process, rocket launches, and a network of terminals and ground stations all over the world.
The satellite industry is $293 billion in size, and it's a huge portion of the global space economy.
The business is also in the middle of a revolution. In just the past 5 years, the number of active satellites in orbit has more than quadrupled, and the economics of building and launching them have changed astronomically.
In the traditional model, you're building one satellite that might cost hundreds of millions of dollars. The cost of launching new satellites is less than $1 million, and they can get a lot more satellites on a rocket.
For the Freakonomics Radio Network, this is the economics of everyday things. I'm Zachary Crockett. Today, satellites. By definition, a satellite is any object that revolves in a curved path around the planet. Technically, the moon is a satellite. But most of the time we talk about satellites, it's in reference to the weird-looking pieces of hardware that we build and shoot into the sky. When the first man-made satellite, Sputnik 1, was launched by the Soviet Union in 1957, it captivated people all over the world.
Today, a new moon is in the sky, a 23-inch metal sphere placed in orbit by a Russian rocket.
Orbiting hundreds of miles up in the atmosphere, it was able to send a radio signal back to Earth for 3 weeks before its batteries ran out. Sputnik was mostly a way for the Soviets to show off their engineering prowess. But as satellites evolved, they found commercial applications.
Satellite has been essential for a long time, dating back to the 1960s when it was first used for transmitting TV signals across the oceans. When people wanted live TV from the Olympic Games in the 1960s, that was done via satellite.
Tim Ferrer is the president of TMF Associates, a space consultancy that has worked with satellite companies for more than 20 years.
Since then, it's evolved into things like satellite TV and other communications. We've seen a lot of interest in broadband services on planes, on ships, in people's homes when they're in remote areas.
On Earth, we have a bunch of ways to transmit information. Telephone wires, fiber optic cables, cellular networks. But there are a lot of places where those methods aren't feasible. Satellites can relay information from one place to another using radio waves.
Typically, a satellite is either a box or a cylinder at its heart, and that contains all the electronics and the processors and what is needed to keep the satellite stable. You usually have two big solar array wings that stick out from the side of the satellite, and then on the bottom of the satellite, pointing towards the Earth, you will have a dish that focuses the signal down onto the ground.
You may have seen one of those enormous satellite dish-looking things on the top of a hill. That's called a gateway, or a ground station. It transmits a radio wave signal at a specific frequency. A satellite up in the sky receives that signal with all of its fancy equipment, then sends it back to Earth, to a network of individual devices, like the satellite dishes and internet terminals you put on your roof.
So Netflix, that's providing you with your streaming TV service, you ask Netflix to send you a show, Netflix puts that onto the internet, that gets routed to an Earth station that's connected to fiber, and it's sent up to the satellite that's going overhead, and then the satellite relays that signal back to me at my home.
Today, there are nearly 12,000 active satellites orbiting Earth. Many of them are used for communication, like satellite internet, TV, and phone service. But they're also used to collect highly detailed Earth imagery, which has its own business applications.
So if you're a trader on Wall Street trading on energy, you might be monitoring progress on a power plant in China. These companies take pictures from space and they track cars in parking lots on certain sites to see how construction is progressing.
Again, that's Rachel Jewett.
Something that people are really trying to figure out right now is how to get better wildfire detection with satellites. They're looking for changes in heat, or it could be a sensor on the ground that's sending its data via satellite.
Global positioning is another big market for satellites. Different countries use different systems, but in the US, we're most familiar with GPS. There are only around 30 GPS satellites in orbit, and they're all owned by the government, which provides positioning data free of charge. Private manufacturers sell equipment like receivers that can more finely tune that positioning.
Farmers are able to use their machines to plant very, very specifically, and they know like the exact inch that something was planted. They have satellite terminals on the John Deere tractors that connect to a different network, and they augment the GPS signals.
Traditionally, most satellites in orbit have been what are called geostationary satellites. They're about the size of a school bus, and they orbit at a high altitude, around 22,000 miles.
Those satellites look to be at a fixed point in the sky, and they can broadcast the TV signals all across the US with just one satellite. They're sufficiently high up above the Earth so that the speed at which they orbit the Earth matches the speed of the Earth's rotation. You just point a dish at the satellite, and the satellite stays in the same place. If you are in the broadcast industry, like if you've got a satellite TV company, then you want to be able to broadcast your service all across the US to lots and lots of people. So those systems are in geostationary orbit.
In the early days, many of these satellites were actually made by car companies, like General Motors and Ford. At one point in the 1980s, Ford Aerospace was responsible for more than half of all communication satellites in orbit. Today, it's mostly big aerospace companies.
Boeing, Lockheed Martin, Airbus makes a lot of satellites. There's a company called Thales Alenia Space that is another big aerospace and defense company in Europe.
A single geostationary satellite can take several years to build. They're incredibly expensive, and they need a lot of testing.
In the traditional model, you're building one geostationary satellite that might cost anywhere from 100 million up to as much as 400 or 500 million. And so you have to be really, really careful. You're using proven materials, things that have been tested in radiation environments to check they're not going to get sort of zapped by cosmic rays. You put it in what's called a thermal vacuum chamber, where you basically take all the air out and check nothing falls off, and you shake it around and check everything's going to stay connected.
During this phase, a satellite also has to get clearance to be in space. Satellites are regulated by the International Telecommunications Union. It's an agency of the United Nations that agrees on certain rules and standards. But each country also has its own internal regulatory body. In the US, that's the Federal Communications Commission. When a new satellite goes up, it has to use a specified part of the frequency spectrum to send signals.
They go to the FCC and say, I want to launch this set of satellites in this frequency band to do these things. And the FCC says, well, you better show me you're not going to interfere with anyone else who wants to do the same thing. They submit a lot of papers and math and engineering calculations. And ultimately, hopefully, the FCC says, sure, go ahead and do that. And then you get your bit of spectrum.
Once it's built and approved, each satellite has to be launched into space on its own rocket. This job is typically outsourced to a contractor, and it can add another 8 figures to the cost.
SpaceX is the biggest contractor for rocket launches. When it comes to what they charge external customers, we're talking about $60 million plus.
Most of these geostationary satellites are owned by satellite operators like SES and Viasat. These companies order satellites from manufacturers like Boeing, pay SpaceX to launch them, and run big ground stations where they monitor and manage their fleets. They make money by renting data capacity to customers.
They're selling to media broadcasters, they're selling to governments, they're selling to cruise ships, airlines, they're selling to mobile network operators to expand the reach of their networks. The cable operators have years-long contracts with satellite operators.
Each megabit per second of capacity can be sold for a few $100s per month. And a large geostationary satellite might be capable of delivering up to 1 million megabits every second. Once these satellites are in space, they typically last around 15 or 20 years, and the clock is ticking on an operator's financial return.
If you spent, $500 or $600 million on a satellite, you'd hope to get back, hopefully, as much as $100 million a year over that period and make a profit. If you don't sell very much of it and it's not such a good investment, you might only get back $50 million or less every year. But that's the bet you're making to pay for the satellite before it reaches the end of its life.
Those bets aren't the only threat to satellite operators' bottom line. These days, they face competition from a new type of satellite. That's coming up. Because they're so high up in space, geostationary satellites have a very broad reach. A single device can cover about 1/3 of the Earth's surface. That's great for something like satellite TV, where the same programming is broadcast to a large number of people. But in the past decade, the media landscape has dramatically changed.
There's not as many geostationary satellites being ordered because more and more we get our TV services from streaming. We get it from Netflix and Amazon and Apple. You have to have thousands of satellites to carry all that traffic because they've got to send signals to every individual user, not just broadcast across the whole country.
That's where a different type of satellite, called low Earth orbit, or LEO, comes in. These orbit as low as 300 miles above the Earth's surface. Unlike geostationary satellites, LEO satellites are always in motion relative to the Earth's rotation. They travel at 17,500 miles per hour and can orbit the Earth in about 90 minutes. They're a lot smaller, anywhere from the size of a shoebox to the size of a table. And there are a hell of a lot more of them.
You need to make sure that if you're going to deliver a continuous signal, you need the next satellite to come along before the other one's gone out of your view. And so it's a game of scale. You need hundreds or even thousands of satellites so that you can always hand off from one satellite to the next one and not lose. The more you can build, the better the economics get because there's more and more satellites to choose from.
In recent years, there's been fierce competition to dominate this new frontier of satellites. And so far, a clear winner has emerged with Starlink, a line of satellites made by SpaceX. The company started launching them in 2019 and already makes up more than 2/3 of all satellites in operation.
SpaceX alone has accounted for 8,000 new satellites being put into orbit.
In contrast to the traditional geostationary satellites that take years to build and test and cost hundreds of millions of dollars, SpaceX manufactures multiple satellites every day at a reported cost of less than $500,000 each.
The low Earth orbit satellites are smaller and easier to make. When you're making them in vast numbers, that allows you to cut back on the testing. So what does Starlink do to test its satellites with the vibration? Well, they stick it on the back of a FedEx truck and send it off to the launch station and figure that the roads going down to Cape Canaveral in Florida are so rough that it's going to be shaken around enough on the way there. And if something's going to fall off, it will fall off. So they lose a few, but they don't need to do all the testing that you had to do with your one-off $100 million satellite.
SpaceX enjoys another huge advantage over the traditional satellite operators: vertical integration. They not only build their own satellites, they also launch them using their own rockets. SpaceX is a private company, and they didn't respond to our request for comment on their costs. But Tim Ferrer says that each launch might only cost them a fraction of the $60 million they charge other operators.
Their internal costs are maybe only $20 to $25 million. Some people estimate even less. And they can do as many as 20 launches with a single rocket, at least the first stage, the bit that comes back to Earth. And that saves a lot of money.
The economics are even more favorable when you consider that SpaceX can split that cost across many satellites.
I talked about the design of traditional satellites. It's usually a cylinder or a cube. Now, Starlink has gone for a novel design where basically they're a big flat rectangle. Starlink satellites are stacked one on top of another, 20 to 30 satellites or more on a rocket. And so the cost of launching each of those satellites is less than $1 million. We're talking about each of those satellites with their 100 gigabits of capacity costing maybe $2 million to build and launch compared to the GEO satellite that has 10 times as much capacity, but that might have cost you $600 million to build and launch. So, 300 times more for only 10 times more capacity. That equation isn't so favorable to the GEO satellites anymore.
SpaceX makes money on its Starlink satellites by selling internet plans that range from $80 for residential customers to thousands of dollars for certain commercial accounts.
Each individual Starlink satellite might only serve a few thousand users, but collectively they have enough capacity for 10 or 20 million users. They have 6 million users today, and they have enough to accommodate growth, at least in a lot of parts of the world.
It's a promising business model, and they aren't the only company doing it. OneWeb has more than 600 LEOs in orbit. Amazon has plans to build 3,200 satellites of its own. And a handful of other companies, like Planet Labs and AST Space Mobile, are also competing for market share. But this huge swell in satellites isn't without cause for concern. Smaller satellites, like those that SpaceX makes, reportedly only last around 5 years, and they constantly need to be replaced.
Cosmic radiation is quite intense up in space, and those sometimes make your computer malfunction. That can send a satellite out of control and kill it very quickly. And the other part is your batteries. With low Earth orbit satellites, they're going round and round the Earth from the dark to the light every 90 minutes, and they're using lithium-ion batteries, generating power from solar. And after a few years, the battery just can't hold a charge anymore.
But the most common cause of death of a satellite is simply running out of fuel.
You have to maneuver the satellite to keep it in the right place in space. And you have to expend a little bit of fuel every few days. So you put enough fuel on the satellite to last a certain number of years. With a geostationary satellite, it might be enough to last 15 years. With a low Earth orbit satellite, you might need to maneuver a bit more, and you might only have enough for 5, 8, 10 years.
We're not quite at the point where we have reliable roadside assistance for satellites in space. But in some cases, operators enlist something called a mission extension vehicle. It's a special type of satellite that latches onto another satellite in orbit and uses its own thrusters and fuel to prolong service. It's not cheap.
It's a few tens of millions of dollars to get this servicing satellite up there to keep it going for another 5 years.
For a $300 million geostationary satellite, it can be worth the cost. For the new smaller satellites, not so much.
We're moving from the geostationary world to the low Earth orbit world where the satellites are becoming more and more disposable. And so people are not likely to do that for a satellite that only cost you $1 million or $2 million in the first place.
Rachel Jewett of Via Satellite says that the expendability and sheer number of these small satellites might pose a risk.
Some people say that there's plenty of space in space. We just need the right traffic management system. But then some people are concerned that it is getting quite crowded. If two satellites collide, they create debris, then it kind of goes into a spiral, basically. That's a worst case scenario fear that people talk about.
In 1978, two NASA scientists laid out a theoretical scenario called the Kessler syndrome. They posited that one day, the increasing density of objects in low Earth orbit could lead to collisions, and these would create a chain reaction of other collisions, ultimately making certain regions of space unusable. So far, satellite collisions are rare, but they have happened.
There was a famous collision about 15 years ago where a satellite collided with a defunct Russian spacecraft and scattered debris all over the sky, and people got very worried about that.
Regulators have imposed more stringent rules in recent years to make sure satellites are appropriately disposed of at the end of their life.
In low Earth orbit, they are deorbited, they are sent down, and they burn up in the atmosphere. And in geostationary orbit, they have propulsion on board and they boost themselves up higher into what's called a graveyard orbit.
So they're just perpetually floating around somewhere up there?
Yes.
But for true space nerds like Rachel Jewett, the benefits still outweigh the costs.
Obviously, we're talking about really amazing technology. It's improving agriculture or bringing connectivity to areas that have never had it before, making, search and rescues possible. What we're really talking about is making stuff possible here on Earth. That's what I think is really cool.
For the economics of everyday things, I'm Zachary Crockett. This episode was produced by me and Sarah Lilly and mixed by Jeremy Johnston. We had help from Daniel Moritz-Rapson. And thanks to listeners Tina Husiao and Adam Blandis for suggesting this topic. If you have an idea for an episode, feel free to email us at everydaythings@freakonomics.com. Our inbox is always open. All right, until next week.
In some ways, it's been a bit like the airline industry. How do you make $1 million? You start with $1 billion.
The Freakonomics Radio Network, the hidden side of everything.
Stitcher.